In this lesson, we will discuss permutations. Before getting into the details of this topic, I need to start with a definition, that of factorial. Let n represent a natural number. If you remember, those numbers like 1, 2, 3, all of the positive integers. If we say n factorial, we mean take the product of all the integers starting with n all the way down to 1. And we're going to denote that by n followed by an exclamation point. So for example, what is 3 factorial? This symbol means take 3 and multiply until you get down to 1. So 3 times 2 times 1. And this product is equal to 6. So you can use this definition for any one of these integers. Maybe we could check out 5 factorial. What's that? Okay, so 5 factorial is, by definition, 5 times 4 times 3 times 2 times 1. Okay, so that is, oh, well, here we have 3 factorial, which is 6, and 6 times 20 is 120. So here is 5 factorial. All right, so maybe one more. What about 15 factorial? Okay, so that is 15 times 14. Okay, this is going to take a long time to write, so I'll just do ... until we get to 3 times 2 times 1. So start at 15, keep multiplying until you end up at 1. And this number comes out to be 1,374,368,000, which is huge. I mean, this is a large number. And this is one of the reasons for using factorial. You can take this number, which takes a long time to write, and you can express it in this very concise way. The second purpose of this definition is, in many mathematical computations, this pattern will emerge where you start at a number and multiply down until you get to 1. So it's nice to have a short notation to represent these numbers over here. So that's the first thing, just the definition of factorial. Another thing to point out about this definition is, and I kind of said it when I computed this here, if you start with 5 factorial, then every factorial smaller than it will appear within the expression, like 5 factorial has 3 factorial in it, and this allows you to write 5 factorial in a couple of different ways. 5 factorial is the same thing as 5 times 4, that was supposed to be a 4, 5 times 4, and then you get 3 times 2 times 1, but you can just call that 3 factorial. So here, 5 factorial is the same thing as 5 times 4, but then instead of writing all of these numbers, you could just write 3 factorial, and you'll end up at the same number of 120. You could also write, well, 5 factorial is equal to 5 times 4 times 3 times 2 times 1, but that's the same thing as saying 4 factorial. So you can always write this expression using smaller factorials after it. The same is true for 15 factorial. You could write 15 factorial as, let's say, 15 times 14 times 13 times 12, and the second you get to 11, well, instead of writing 11 times 10 times 9 and so on, you could just put factorial after it, and this symbol is the same thing as saying, okay, put 10, then 9, then 8 until you get down to 1. So a nice observation about working with factorials. So the definition, different ways that you can write it. The other thing I'd like to look at is, what if you take numbers like this and you divide them? How would those simplify? Let's try out this. What if you take 5 factorial and you divide it by 3 factorial? How would this simplify? Now, certainly, you could just take 120 and 6 and divide those two things and get a number for it. Instead, I'd like to write out the definition of both 5 and 3 factorial in a fraction, and I want to see what that looks like. So in our fraction, 5 factorial is 5 times 4 times 3 times 2 times 1. In the denominator, 3 factorial is 3 times 2 times 1. Notice that this simplifies really well. The 3's will cancel, the 2's will cancel, technically you can cancel the 1's, and all of these things left over are just 1. In fact, the denominator completely cancels, and you're left with 5 times 4, which is 20. So that is the answer to this. It's 20. Another way you can think about this is 5 factorial is this. it's 5 times 4 times 3 factorial. So you could say, all right, it's 5 times 4, and then you put a 3 factorial at the end. This is even better, because if you leave the denominator completely alone, here you can just completely cancel the same thing from the top and bottom, the 3 factorials. You get 1's left over, you have 5 times 4, which still takes you to 20. Likewise, what is, as a second example, what is 15 factorial divided by 14 factorial? What would that be equal to? Well, in the top, you get 15 multiplied all the way down to 1, and in the bottom, you have 14 multiplied all the way down to 1. The top is 15 times 14, but if you put a factorial after the 14, well, that will take you down to 1. You can leave the denominator completely alone. It's also 14 factorial. And now those things completely cancel. They're 1. And the only number you have left over is 15. So if you take 15 factorial, divide by 14 factorial, it's just 15 left over. Let's try let's try one more here. What if you had, how about 8 factorial divided by 6 minus 2 factorial? What is that? In the top, I have 8 multiplied all the way down to 1. Now, in the bottom, this is an order of operation problem. We have parentheses. Before we can apply the factorial, I have to know what 6 minus 2 is. So if I see this expression, well, 6 minus 2 is 4. Okay, so this is equal to this. These now resemble these other fractions that we are working with, so I'll continue this work over here. 8 factorial, since it's 8 multiplied down to 1, you could write that as 8 times 7 times 6 times 5, and the second you get to 4, you could call the remaining stuff 4 factorial. That is perfect because it'll completely cancel with the 4 factorial that's in the denominator. This is 1 and this is 1. We're left with 8 times 7 times 6 times 5. 6 times 5 is 30. 8 times 7 is 56. Okay, 56 times 30 is 1,680. And that's what this expression simplifies to. So that is the definition of factorial, so things like this here, plus different ways that you can write them as well as simplify them. Let's see how this definition shows up in the topic of this lesson. So on to the definition of a permutation. A permutation is a way in which a number of objects can be ordered where each object is used exactly once. Let's use example 1 to understand this definition as well as come up with a formula for computing permutations. So here in example 1, let's say you have 3 books that you'd like to place on a bookshelf. And they are Ralph Ellison's Invisible Man, which I'll denote by A, Herman Melville's Bartleby the Scrivener, I'll denote by B, and then Suzanne Collins' The Hunger Games, which I'll denote by C. Let's start with this first question. In how many ways can these books be ordered? So how many ways can you order A, B, and C, which again stand for 3 different books? Well, on your bookshelf, you could first put Invisible Man. So you could denote that by A. This is taking the first spot in your bookshelf. And then with the other 2 books, there's 2 possibilities. You could say, well, maybe I'll just do Bartleby the Scrivener and then The Hunger Games. Of course, there's one other way that Invisible Man can be first, and then you can order the 2 other books, and that's if you swap the location of these 2 things. So you would have Hunger Games second and then Bartleby last. So here's 2 possibilities. These are 2 ways to order your 3 books. Now, as another possibility, it could be that Invisible Man will be second on your bookshelf. So after you get done with those 2, maybe this one goes in the middle. Well, it could be that Bartleby the Scrivener is to the left, and then Hunger Games is to the right. Or, again, assuming that Invisible Man is second, maybe it's that you first put the Hunger Games and then you put Bartleby the Scrivener. So again, okay, now we have 2 more ways. The only other option is if you put Invisible Man last. Now, you could first have Bartleby the Scrivener, and then you could have Hunger Games, or you could first put Hunger Games, then Bartleby the Scrivener, and Invisible Man is last. This is every single possible case because either Invisible Man is first, second, or third. So how many things do we have? We have a total of 6. So 6 unique ways in which these 3 books can be ordered on your bookshelf. It would be nice if there was a formula that told us this number so we didn't have to actually list them out, especially if the number gets larger. If you had 20 books, it would take a very long time to list out every single possibility. And it turns out there is a nice formula for this. The number of ways that you can order n objects, like in this case we had 3, the number of ways which that can be done or that can be permuted is n factorial, the thing that we were talking about in the previous slide. Does that actually match up with the answer that we got here? It should be that the answer is 3 factorial. Is 3 factorial equal to 6? Yeah. 3 times 2 times 1 is 3 factorial, and that does in fact multiply to 6. So this formula can save you a lot of time, and it will work for every single number. Now, the first question is, well, why does that work? Why is this formula true? There's a nice, easy argument for this. On your bookshelf, you have 3 locations, the first, second, and third spot. What we're going to do is use the counting principle from the previous lesson. How many choices are there for this first spot? Well, if you haven't made a choice yet, you're choosing from 3 books, so there's 3. It's 3 possibilities. Now you move on to the second spot. How many choices do you have for this spot here? Is it 3? No. The reason it's not 3 is, well, you already put a book here, so you took 1 out of circulation. There's now only 2 choices left. You can only put 2 books here. Because you used 1 up here, there's 1 taken away from the size of your group, so there's only 2 possibilities of books that can go here. Now here's your last spot. How many choices for books can go here? Is it 3? Is it 2? No, it's only 1. Each time that you move along, the number of choices you have drops down by 1. The counting principle from the previous lesson said, if you take these choices and you multiply them together, that gives you all of the possible outcomes, which in this case is 3 factorial, and it's the same thing as 6. And that's why this fact is true. Now this is nice because, sure, for 3 books, easy enough to count without using this formula, but if you had 4 books, I still think you could do this. You can try it if you want. It's just faster to say the number of ways that you can order is going to be 4 times 3 times 2 times 1, which is 4 times 6, and that's 24. What if you had 15 books? If you had 15 books, well, the answer is 15 factorial. I stated that number on the previous slide. I think it was 1,307,674,368,000. So, I mean, having 15 books on a bookshelf isn't unreasonable, and this is the number of ways that you could permute them, where each object, each book is placed exactly once, and the order in which you place them matters. All right, so let's expand on this idea in the next example. Let's now generalize the ideas that were in the previous slide. In the last example, we said there were 15 books on a bookshelf. The number of ways that those could be permuted is 15 factorial, and it was a very large number. But maybe you don't want to permute every single book. Maybe there's only 10 that you'd like to permute out of the total of 20. So you want to leave 5 alone and then permute the rest. Well, how many ways can that be done? We can't use the formula on the previous slide. And in fact, we're going to need a new formula. We're going to denote this formula by NPR. You can read this as N permute R, where N is the number of objects that you have, and R is the number of those objects that you want to permute. So just to state that again, for this formula, the number of ways that you can permute R items taken from N objects is given by, I think I'll first state the formula. It's N factorial, but you divide by n minus r factorial. To answer this type of question, if you know n and r, you can plug them into this expression, simplify it, and it will give you your answer. I'd like to use example 2 to demonstrate why this formula is true. So let's see if we can actually answer it without the formula, and then we'll go back and plug in numbers to verify that the formula works. This says the 100 meters at the Olympics is a race between 8 runners. If we are assuming there are no ties, in how many ways can the first 3 finishers come in? To start this problem, the total number that we're considering is n is equal to 8. But the answer to this problem is not as simple as saying, oh, it's 8 factorial. Instead, what we're saying is, of these 8 runners, in how many ways can we permute 3 of them? Let's first start by using the counting principles we have. There are 3 spots for first, second, and third. How many choices do we have for the first spot? Well, we haven't chosen anyone yet, so we still have a total of 8 people. So I'll put an 8 here. Now, how many choices do we have for the person coming in second? Well, there were 8, but 1 was taken away for first place, so now there's only 7 choices left for second place. And then lastly, well, how many choices are there for third place? There's 1 here and 1 here, so of the 8, there are only 6 remaining. So the answer is, it's 8 times 7 times 6. Now, that's not a factorial, but that's still something we can multiply. 8 times 7 is 56 times 6 is 336. And that's the answer. Now, why does that relate to this formula here? If you understood how all of this worked, you could say that, well, if n is 8 and r is 3, the answer we're looking for is 8 permute 3. And according to this formula, I'll put an 8 here, an 8 here, and I'll subtract off 3. So that's 8 factorial divided by 8 minus 3 factorial. If we simplify this thing, I'll leave the top as 8 factorial for now, and in the denominator, I have to first do 8 minus 3, which is 5, and that's 5 factorial. If you're looking to cancel 5 factorial, you have to split that off of 8 factorial. I'll multiply 8 down to 5 and call the remaining 5 factorial. It looks like this. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is 5 factorial. I can now cancel the factorials between the numerator and the denominator. They're equal to 1. And what do you know? The amount left over is just 8 times 7 times 6. Not only is that 336 the answer that we are looking for here, but it perfectly matches up with the way we argued it here. So technically for this type of problem, there's 2 valid ways to answer it. You could use method 1. I'll call this method 1, where you can just use the counting principle. And then the second method, I'll say method 2, uses this formula. Both are equivalent and will give you the same answer. In our last example, we are told a cinema is running a horror film festival on Halloween. They plan on showing 13 movies, and they have 20 to choose from. How many lineups are possible for their festival? The way I view this is we have 20 movies to choose from, so that's the total, which we called n, but we're only going to choose 13 of them. But not only are we choosing them, we're ordering them in a particular way since we're talking about lineups. So here the order matters. This means we can use the formula on the previous slide. That is 20 permute 13. And the formula said you take 20 factorial, but you divide by 20 minus 13 and take factorial of that number. The top is 20 factorial, and the bottom is 20 minus 13, which is equal to 7 factorial. Now, in the top, we have to multiply 20 until we get down to 7, and then it's 7 factorial from there. I guess I'll write this out. That's 20 times 19 times 18 times... I think I'll do a dot, dot, dot to indicate that we eventually get to 9, then 8, and then 7, but we have 7 factorial. And this is all divided by 7 factorial. It's valid to use this ... mathematically. If you know the pattern and the pattern's clear, it just makes writing things shorter. So 20 times 19 times 18 until we get to 9 to 8. And this is the thing we're looking to cancel. 7 factorial cancels with 7 factorial. Those are both 1. What is left over, 20 permute 13, is 20 times 19 times ... until you get to 9 and then 8. In this case, I would not do this computation by hand. This is something for a calculator. In fact, my calculator has a factorial button on it. I'm going to type in this expression just because it'll be faster than writing this in. Okay, so the number I get... Wow, okay, so this is 482,718,652,416,000. All right, so that's millions, billions, trillions, 482,718,652,416,000. That's a lot. So that's the number of ways that given 20 items, you can permute 13 of them. So I think for this problem, because the number is so large, that this formula is probably the best way to go. If you want to use the first method that we had on the previous slide, you'd have to put a total of 13 categories in a row. So you'd have to have 13 lines like this. So you go until you get to 13. And then the choices for the first spot would be 20, then times 19, 18, 17, and 16. And what you'd see is you actually end up with this expression right here. 20 multiplied all the way down to 8, which is 13 total spaces. So whichever method you choose, both will work. But in some cases, having a formula is great just because if you can enter this into a calculator, it'll save you a lot of time to get the final answer. So that is it for this example. Now, just in case you're curious, I wanted to discuss a couple of things about factorial. So we define factorial as you start with the number and multiply down until you get to 1. So trivially, 1 factorial would be 1. 2 factorial is 2 times 1, which is 2. 3 factorial, 3 times 2 times 1, that is 6. That's a 2. And then 4 factorial, you multiply down until you get to 1. And so that is 24. Notice that every time that you go up in factorial, you're multiplying by the next number. So if you want to go from 1 factorial to 2 factorial, so if you want to go from here to here, you would multiply by 2. To go from here to here, you would multiply by 3. And to go from here to here, you multiply by 4. You can reverse this process too. So if you want to go from 4 factorial to 3 factorial, you wouldn't multiply by 4, but you would divide by it. If you want to go from here to here, you would divide by 3. You want to go from here to here, you would divide by 2. This takes me to, well, what is the definition of 0 factorial? It doesn't really seem to fit into the formula that we have. But it turns out you can define it. If you follow this pattern here, if you want to go from this number to whatever this number is, you would have to divide by 1. So if you go from here to here, you would divide by 1, meaning you take 1 and you divide by 1. What's 1 divided by 1? It's 1. You can check this fact in a calculator if you'd like to. If you enter in 0 and type in factorial, it's going to tell you 1. And the reason for it is the pattern that I described here. So not only has factorial been defined to include 0, it's been defined to include a lot of other numbers. In fact, the generalized formula for n factorial is equal to, and don't worry about this notation, it's the integral from 0 to infinity of t to the power of n times e to the negative n plus 1 dt, whatever all that means. But it's interesting that with this formula, you can now ask the question of, well, what does it mean to be 1/2 factorial? And it turns out there's an answer for this. The answer is the square root of pi over 2. So if you ever find yourself studying advanced mathematics one day, maybe you'd encounter this. But I digress. The other thing I wanted to mention is, if you recall on the lesson from trigonometry, I said that sine was equal to the following polynomial. It was x minus x cubed over 6 plus x to the 5th over 120 minus x to the 7th over 5040. And I think there was one more term I had. It was x to the 9th over, I believe, 362,880 and so on. What are these numbers and where do they come from? These numbers are actually factorials. This 6, that's 3 factorial. This 120, that's 5 factorial. Do you know what 5040 is by any chance? 7 factorial. And this one is 9 factorial. It turns out that the factorial number in the denominator corresponds to the exponent on the powers of x's. And it creates this really beautiful pattern for the function of sine of x. You could write this as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. It goes on forever. You know what the next term is? Obviously x to the 11th over 11 factorial. And furthermore, going back to the first one here, there's technically an exponent of 1 on this x, and you can divide this thing by 1 factorial because 1 factorial is 1. So it's pretty incredible that sine has this really nice pattern for its polynomial. There's one for cosine, tangent, and also for other functions like logarithms, exponential functions. But that all said, I think I'll leave it there, and that's it for this lesson.